guess you guys are ready. Okay, so while I have talked about legs so far, I promised you when we started that discussion, the reason to choose legs was because I think there's some beautiful, simple systems that are interesting to study, and there's a subtle thing, which is that we can talk about stability of periodic motions in a nice way with legged systems. But actually, a lot of the ideas we've been talking about, for those of you that care more about manipulation, for instance, those ideas are perfectly relevant too. Today we're going to do some of the algorithms that extend our basic ideas of trajectory optimization and Lyapunov and the like to the problem of analyzing a stable limit cycle of a walking robot. But I'll try to convince you as we go along that this is just as relevant for manipulation, and I'll give you a few manipulation examples as well. Okay, so what we want to do is take the ideas that we've started on with our toy models, and first we looked at just the passive dynamics of those models, the nonlinear dynamics of the rimless wheel and the compass gate, for instance. And then we talked about some simple control, just like we did in the Acrobat and Carpal. We talked about Mark Spong's swing-up controller, and we talked about Mark Rabert's hopping controller, for instance, for the legged robots. But all of those, I think, are great, but we want to use algorithms. For the general purpose, I've got a new robot, or I put my robot in a new environment and I have to solve it, I believe algorithms are the way to go. So let's see if we can extend our trajectory optimization and other tools to the problem of walking robots today. Okay? I still want to use the rimless wheel and the compass gate and the others as our linchpin examples to help us make sure we can draw two-dimensional plots and understand what the algorithms are doing. So let me remind you that the rimless wheel which was the pendulum on a ramp, basically, right? Pendulum rolling down a ramp, right? It had a stable periodic cycle. If we plotted it in theta versus theta dot, then there's, I wrote the dynamics so that 0 was the upright. There's a sort of notable thing that happens here when you smack it, when your one foot smacks into the ground at gamma minus alpha. And then another thing happens over here when your front foot hits the ground. That happens at gamma plus alpha. Just to remind you, gamma is the slope, alpha is the half angle of the legs. Okay, so the compass gate, because I have penetration in any other condition, in any other configuration, it lives inside the range of theta being from gamma minus alpha to gamma plus alpha. Inside that, it's governed by the standard pendulum dynamics, which have the homoclinic orbits that look like this. And we found, with a little bit of solving equations and writing out the map, that there is a neat place right around here where the rimless wheel goes down, comes back up, but then on impact it loses exactly the same amount of energy that it gained by this asymmetry, by going down the ramp, represented by that asymmetry, the fact that this leg of the journey is longer than this leg. So it leaves with more velocity, but it loses some velocity, cosine of 2 alpha, if you remember the derivation, as it slams into the ground. Then we rejigger the coordinate system so that theta is on the new foot, and effectively transition like this, and we have this stable limit cycle governed by that, right? Where this is just the instantaneous impact that takes us back and resets the coordinate. Right? Do people remember that picture and feel pretty comfortable with that picture? Okay. So the rimless wheel is sort of the only example that I can give you, and the slip was, with a little bit of linearization, was maybe the other example, where we were able to find that limit cycle in closed form. Right? We could actually describe that curve. First of all, I know that I have a closed form solution for this, well, partly because the energy is just constant in the passive walkers, but also I can find the fixed point of that analytically because I was able to perform the integration across this cycle, and we were able to do things in closed form. For even the compass gate, we couldn't do that. I couldn't do that. So, so how do you find the limit cycle for the compass gate, right? The answer is you start doing numerical optimization or numerical search. In this problem, if you had a function which just simulated your system across one cycle based on some initial conditions, you could do an optimization algorithm that just searched for this initial theta dot, then moved this up and down, simulated until I found the zero of that map. That's a perfectly reasonable thing to do, and that's what people sort of used to do. But now that we understand how to do trajectory optimization on these systems, it turns out the more general approach to finding these limit cycles is with trajectory optimization. That's true even in the passive system, but the reason it's more powerful is that if I go to controlled systems, like the compass gate, I talked about as a passive walker, but the simplest control problem we have sort of in walking robots is when you take that compass gate and you suddenly just add a torque at the hip, and you'd like to ask, what are the stable solutions of that where the torque may not be zero over time? I might be able to apply a time-varying torque. Now I can do trajectory optimization to try to find controlled limit cycles, or controlled periodic solutions at least, okay? So how do I do trajectory optimization through contact? Okay, that's step number one. We already know how to do trajectory optimization for acrobats and cart poles. The way that I advocated is my favorite, but not the only one, is this, were the algorithms that were based on direct transcription or direct collocation, right? So, so you remember before when I had a problem x dot equals f of x u, and I wanted to find some trajectory that was of interest, maybe that started at the bottom, ended at the top, minimized some cost function. Then in direct collocation, I was able to formulate an optimization which said minimize, for instance, the sum over my time samples of some cost function, which I can replace with actually the decision variables of that optimization at each knot point, subject to the direct collocation constraints, right? So I'd like that the cubic spline derived by this enforce, you know, that roughly x dot equals f of xu. So the key was that in direct collocation I was looking over both x's and u's, right, in order to do that optimization. So I had decision variables that, for instance, in this problem would be moving along the trajectory. In the passive case, I don't even have u, so I just have decision variables that are along the trajectory. My goal is to write an optimization that satisfies the dynamics at all places in time. That's easy. That's the same direct collocation. But I could, any of these orbits would satisfy that. Any solution of the, that's like writing an integrator for the rimless wheel. How do I help it find the periodic solution through impacts? Okay. Well, direct collocation and optimization, especially nonlinear optimization, is very generic and very powerful. So all I have to do for this, for the rimless wheel example, is to throw in a few more constraints, right? So I could say, for instance, I'd like to say that x0, you know, has the property that the, let me even say theta dot 0, theta 0 is equal to gamma minus alpha. I can put a constraint on the decision variable, which represents the first point in my trajectory, and say I'd like it to be somewhere on this line. right? I want it to be at the event that just happened from collision. Yeah?
Is this for fixed gamma alpha?
Gamma and alpha are constants in this case, yeah? That's the...
If you want it to be periodic, but don't particularly care what the period is.
I am not enforcing the period in any way. This is the geometry of the problem. This is the interleg angle and the slope of the ramp. So once you have a robot, you have these. I'm not enforcing the period. I think I know where you're going, but let me. Okay, that's a good point actually. Let me get back to that in just a second. So, okay, of course I want the last point in my trajectory to land on this side, right? So I can say theta final equals gamma plus alpha. And there's one more condition. That'll find me any sort of solution that starts here and ends here. But to make it all work, I'd like to embed the impact equation in the constraints. So I have one more constraint which says that theta dot at 0 had better equal cosine of 2 alpha times theta dot at final. So I've put in explicitly a constraint saying that my solution satisfies the impact equation, and that same thing says the solution has to be periodic. Right? I ended after the impact equation back where I started. Okay. Voila, we have a perfectly good optimization problem. Now, your question was on point. So. I've often, when I've written this, implied that these knot points were somehow some fixed time step apart, right? But in fact, the way I implemented in the code, I might have even forgotten to say it before, is I actually had the time intervals in, as decision variables. You call it dt or h as also decision variables. So you're allowed to put. These decision variables need not be fixed in time. They can spread out over time. So if the duration of this trajectory is not known, that's okay. It's also being optimized. Typically, in order to do that and keep it numerically good, I also put in a constraint saying, you might have seen it in the code, all time intervals equal. Right? So I'd like to say that h1 equals h2 equals to hn, so that I don't get all my points right here, and then one jump, boom, over there, which is a poor representation of the dynamics, right? I'm going to say, you're allowed to stretch and shrink. You have to end here, but be uniformly sampled. You can put, upper bounds on those things to enforce accuracy, too. Yeah. Yeah. So it's not always obvious how to do that. The direct collocation constraints, in a subtle way I mentioned before, give you sort of a third order accuracy. But relating that to your differential equation is the topic of numerical analysis. I just pick 0.1. It's all good. Yeah, don't go bigger than 0.1. Yeah?
Could you lose a little accuracy, or not accuracy, with power by doing that? Because if you allow the time intervals to be varied, you might be able to say concentrate where it's more difficult numerically, at the second grade, possibly.
True. Yeah. So that is true. You can if you are willing to. If you don't want to write this down, and you want to think about somehow a way to write that down so that they're closer together at the stiff parts, then you can certainly. The language permits you to do that, but writing that down in a robust way takes some thought. Yeah. Okay, so this is all typed in, but it'll just make this plot, so I guess it doesn't really matter. But it's like 3 lines more than what we did before, which is just adding these constraints that enforce periodicity and enforce the impact equation. Yeah. Okay, so trajectory optimization rules, right? You can throw in really hard problems, including collision, and it still works. Or but sometimes it can't find the solution. But when it's good, it's great. Okay, but this is the specific form for the rimless wheel. Can we generalize it to more complicated robots? Can we generalize it to, say, a hand coming down and picking up a cup, right? Now, so a lot of people in manipulation research talk about planning or trajectory optimization. Most of them commit a sin, right? They don't actually touch the damn object, right? So it's like they do all this trajectory optimization to go up to here, but then they turn it off and then close their eyes and close it like this, right? So there's a lot of good work, but it's all good. But to make sure you don't slam your elbow into the wall because you've got to you have a hard enough planning problem just to make sure your hand gets to the place you want it to be. But a lot of time when people talk about, when you hear manipulation planning, it's often not actually planning through the contact, right? Picking this up and actually forcing the change, a change in the state of the object. For our system, if we write the differential equation that describes both the robot and the object, then the equivalent of this trajectory optimization problem, where you include the contact dynamics between the hand and the object, and ultimately maybe have a new goal for the object, that's the interesting planning problem where the dynamics start to matter and the impact on that dynamics. So when we talk about planning for manipulation, we're going to actually move the object. Yeah? Okay. So in order to get to those pictures, even the compass gate, I need to give you the more general view of these optimizations, and that's the picture you have to have in your head is this picture of hybrid systems. Okay. Okay, so in general, I'm always optimizing some trajectory, okay? And this trajectory may be governed by some differential equation. I'll even leave off the u for now, but it doesn't really matter. And then when I have an impact, just like the rimless wheel when I smacked into the ground, there is some sort of states. This is my plot is in my abstract state space of the world here, okay? There's some place in state space where I have a collision that I need to think about. My foot hit the ground is a good example. Right, so think about my robot foot coming down through the sky. Right, there's a set of configurations when the heel starts hitting the ground. If I were to draw that set of configurations in state space, I've got some set of points when that first contact happens. Okay? It's almost never a line, but for today I'll make it a line just to keep that picture simple. Right? This is going to be a curve because it's going to be in the configuration space, but it's a line. Okay? At that point, something discontinuous happens, and I end up going through some impact equation, which is a discontinuous change in the configuration or in the state space of the robot. Okay, afterwards, I'm in a new dynamical system that I'm now in contact with the ground. I've got my stance phase dynamics. Okay, and then I proceed here with my new dynamical system. Let's call this one F1 of x, this one F2 of x. Okay. Oftentimes, we use the notation that this set of configurations where the system collides is governed by some it's defined implicitly by a function, the zero set of a function, okay, and typically I'd want phi of x greater than 0 over here, and then when it hits 0, I've got a collision. So the standard choice for that would be, for instance, the distance function to the collision, or the signed distance function. You'd like it to be negative over here. You know what I mean by signed distance? It's a kind of a, like, if you stop and think about it, it's kind of a weird name, but I mean, I want a value that is positive when I'm above the ground, and if I were ever to be in penetration, I'd like it to report the distance, but with a negative sign in front of it, okay? Okay, so this event is also called the guard in hybrid systems world. Okay. This thing guards this hybrid transition. And then the update equation, x plus is some function of x minus. That's my impact dynamics. And that's often called the reset map. Okay, so for a system that has exactly two different modes and undergoes only a single collision, this is the picture you want in your head. But you can certainly imagine generalizing this to more complicated situations where I have many possible collision events, right? So in this system, for instance, I'm going to have at least one event when my heel strikes. I'll have another collision event when my foot hits when the front of my foot hits the ground. Right? The toe hits the ground, call it toe strike, right? And then I'll have another event when the heel comes off the ground if I'm doing normal walking, and then I'll come off, right? So there are many different transitions, which is just, another set of pictures like this. Okay? So what's the more general way to do trajectory optimization through contact? Well, if I have explicit parameterizations of phi, right, of F1, of F2, and if I'm willing to know that to decide a priori which modes I'm going to be in what order, that's a big one, okay? I'll try to say that again, but I have to know that I'm going to have a few points in F1, in mode 1, let's call it. If F1, this is also, we have guard, reset, and sort of each individual dynamical system is called a mode in the hybrid systems world. So if I know my mode sequence, I know I'm going to have a few points in F1, and then a reset, and then a few points in F2, then I can write down a trajectory optimization very naturally, just like I did for the rimless wheel, but only a little bit more generic, right? So then I can write down minimize, xi, ui, hi. I'll keep that, including that. That was a good idea. Let's say I'm going to have for all I in 1 to k, I'd like x dot to equal f1. And then for all I k plus 1 to some other bigger number n, x2 xi dot equals f2 xi, right? And I'd like to write the constraints that x k plus 1 equals the reset from 1 to 2 of xk, right? And I'd like to make sure that that phi of xk equals 0. And you probably want to say for all, you should, for all I equal 1 to k minus 1, phi of xi greater than 0. So you don't have a premature, unexpected collision. And so on and so forth. But you can just start adding these up, and given I know that I'm going to be at F1 for a little bit, and then I know I'm going to be F2 for a little bit, and so on and so forth, that's all good. Did you have a question?
Yeah. Is it possible to have I can't think of a walking example, but more than 2 modes?
Yeah, absolutely. So, well, here's the rub.
You work with that.
How would phi work with that? Yeah. I have phi 1, phi 2, phi 3. So the picture you have in your head, let's say in walking, if I'm on the stairs, for instance, maybe I won't do it right now, but if I'm on the stairs, then maybe I have phi 1, which is I land straight on the ground, phi 2, which is I landed on the stair, right? And so there might be a different place here that's phi 2 of x equals 0, and positive over here. And I could have ended up hitting this one first or hitting this one first. But in the formulation I'm talking about so far, you have to decide that, you have to preordain that, right? I'm going to decide ahead of time that I want to hit this one, and then I can write all the constraints. I can even add a constraint saying I didn't hit this one before, okay? But you just start adding these things up and you can write a pretty general problem.
Or else if you're, like, another example would be if your model is sliding, right? So even on a flat ground, if your walking model is sliding rather than staying still.
So the sliding can usually, can you do orbitals on that one?
You can. It's limiting, right? So in the walking example, knowing a mode sequence is equivalent to saying I have, let's say, swing phase, and then heel strike, and then toe strike. And this is sort of reasonable for nominal walking, but it's also a constraint on the solutions I can possibly find, right? Heel off, to toe off, to swing, right? Something like this. That feels like a natural thing to write if you've got a flat foot with 2 contact points, right? But it starts getting painful. Let me go completely out of order, but I actually had a motivating example at the end for this. Here's the place, so we did this, and the whole community sort of did this for a long time, and got pretty far with this. But we started getting more complicated robots, and it was no longer good enough. It became impossible to guess the mode sequence. And let me skip all the way to the end here. So this is a beautiful robot that was designed at IHMC. The picture credits on the previous one, I missed it on this one, I guess. It's called Fast Runner. It's an ostrich. It's supposed to run at 50 miles an hour. And it even plays audio when it's not supposed to. Holy. Ah. Okay, so this is the prototype behind that. Okay, so IHMC is Gary Pratt's group down in Florida. There's a fellow there named Johnny Godowski who's a brilliant guy. He's a builder too. He's a prototyper. He put this together as a ostrich-like leg. Okay, and that leg is moving with its end effector achieving nearly 50, or like it was 30 miles an hour in this one, but he had a later one that was 50 miles an hour. So roughly a robotic ostrich that could run 50 miles an hour. But the cool thing is this one was powered only by his hand. Okay, he was just going like this at the top. But the nonlinear dynamics of that ostrich leg were such that it would load some springs, it would shoot forward, right? It would, there's the number of rubber bands, there was actually, let's see, what's the medical tube called? Whatever, the stretch tube that they use in medical applications, where that was one of the springs. There's the number of clutches and little latches and catches that made that thing work, sort of mind-blowing. But my God, it's beautiful, right? And right, that's just his hand. And basically with one motor at the hip, you can make a robotic ostrich that runs 50 miles an hour. The super cool thing is that it's actually open loop stable. So you start going like this with the real ostrich, and you can make it run over rough terrain to a little extent, and it would actually stabilize. Okay, there was something just brilliant about the way Johnny thought about that problem, that he found this mechanical system that captured running in a beautiful way. The problem is the dynamics were so rich, let's say, complicated, that if you wanted to do anything except run straight, then we had no idea what the robot was capable of. If you had to take a step over something, or go up a stair or anything like that, so we ended up starting to do trajectory optimization to just understand the capabilities. Could you, given you only had a single actuator at the hip, could you use that actuator to, for instance, change the step length? And to what extent could you change the step length over a single interval? Okay? But now let's think about the hybrid mode sequence of that, right? to decide the hybrid mode sequence for that, I'd have to decide which rubber band hit which spring, hit which clutch first. I think we did, we evaluate, there's something like, because it's all combinatorial, so there's something like, 2 to the 12th possible modes that system could be in, and many of them actually it probably was in, and not all. But, but it was so complicated that our existing tools just didn't work. And maybe the picture that I had in my head when we were thinking about that was, this beautiful picture of I've got a line that I'm going to smack into. It looked more like this. It was like this maze of possible collisions that you could have had, and there was complexity in there. If you hit that rubber band first, it would go this way, but if you hit this rubber band first, it would go that way, right? So it was just a mess of possible guards and resets, to the point where hybrid modeling of that system was no longer practical. And so there are ways to generalize this and try to search simultaneously over the mode sequence. I wasn't going to cover that today. That was sort of a preview, but if we get to part 2, then I'll tell you some of those. But there are ways to generalize it. It's just the numerics are not quite as good, and we figured out, the field has figured out ways to generalize that. But that was a good question. Okay?
Question?
Yeah.
So we don't put any Ks in this particular scenario.
True. It's instantaneous. So that is in the rimless wheel example, K is when the instant the foot hit the ground, the same instant, I would call that, T minus, right? T collision minus. And then K plus 1 in this case is T collision plus, the same instant in time. The positions actually have to be the same. For physical impacts, the reset map has the case that the position variables will be the same, unless you do something like reset the angle of your rimless wheel. It's just instantaneous change in velocity for mechanical collisions. Good question. Right? Okay, so trajectory optimization can be extended nicely through contact. It gets increasingly, the chances of you getting stuck in a local minima, I think, go up every time you add another one of some big nonlinear function to your equation. But in practice, walking robots we've been able to do lots of different walking robots optimizing, sort of using this type of technique. If I now go back to the beginning. Yeah, so here's sort of a little, that was the contact model of a robot picking up a ball. This was Spring Flamingo, which was one of the first walking robots from the Leg Lab. And then here's Fast Runner doing optimization. That's the MATLAB version of Fast Runner. And we started asking the question, could you find the nominal limit cycle? The answer is you could. Could you make it go up terrain? It turns out you could. Could you go down terrain? It turns out you could. Was Fast Runner capable of doing foot placement? It turns out it was, right? But it took trajectory optimization for us to be able to answer that question. Okay, so once we have the ability to find trajectories which accomplish a certain task, again, I like the periodic solutions because I can use the language of stability to talk about it. But if this is a one-time, the manipulation example was just I had an initial state and a target state, and I had to find just a single trajectory. It didn't have a periodicity constraint on it. Same tools work. But let's start asking, if we want to talk about how robust that trajectory is, then I can start asking questions about the region of attraction or stabilizing that trajectory, right? Can we extend our tools for trajectory stabilization to the hybrid case? Can we extend our tools for Lyapunov analysis to the hybrid case? Here we go, okay? Friction is a pain point too. If you start having to slide and think of that as a different mode, it was a good point to bring up. It starts getting more and more complex as soon as you have to decide if you're sticking or sliding. Okay. how do you do Lyapunov analysis for limit cycles? And it pays to do the non-hybrid limit cycles first. So for instance, if you wanted to talk about the van der Pol oscillator, right? There was a stable limit cycle of the van der Pol oscillator. We know from simulation that it started out here and would converge, started in here, it would converge. What does stability analysis of that thing look like? Right? What is the notion of a region of attraction of a periodic solution? Okay, so intuitively, what you'd like to do, it turns out that the region of attraction of this one is global except for the origin. So any trajectories here will get back. So that's sort of simple. But, you know, the picture I want you to have in your head is just like I had a region of attraction around the fixed point of, let's say, the pendulum under LQR control. I might have some set of states that are sort of enveloping the nominal limit cycle, right? I wish I brought my other chalk, but is that sort of clear? Like, the picture you have in your head is that there's probably some states that are in the vicinity of the limit cycle that will converge, and maybe if you get too far away, you might go off and do something different, right? So the notion of region of attraction has a natural notion in the context of a limit cycle. How do you find it, right? So, well, you should be able to guess at least one way. How do you think you'd find that limit cycle?
Trial and error.
Trial and error, yes. Lots of simulations, that's a good, I mean, that is one way to do it. Yeah, for 2 dimensions, it's probably fine. The major tool we have for limit cycle stability analysis so far has been Poincare maps. Right, so what does the Poincare map tell us about the system? Right? So if I'm able to write Poincare map, which in the van der Pol oscillator we picked this as the surface of section. That was the map that took us from this point to this point to this point to this point and converged on the nominal limit cycle. Then I can find, if I can find a region of attraction in XP, then I can find the set of points on that surface of section, which I know under the dynamics of the map will converge to that fixed point. The problem is you have to have an analytical description of P if you want to use any of the tools we've talked about so far. If you want to write down and check the Lyapunov conditions by hand, if you want to call sums of squares, you're going to need to have the closed form solution of P for that to work. Almost never do you have the closed form solution of P, not even for the van der Pol oscillator. Right? I have to integrate across that map to figure out what the next point of P is. So my normal tools aren't available yet. If they were available, and if I was able to find this solution, then this solution does actually tell me the total region of attraction. If I were to simulate forward a point from that boundary, it would actually carve out the inner approximation and the outer approximation. There's a beautiful correspondence of the map to the original space. Yeah?
What if you have more dimensions and you don't just have 2 boundaries?
Is that right? Yeah, no, this is only in the 2D, right? So we're going to talk about tools that will work in higher dimensions. Yeah, that picture is only relevant there. Good call. Okay, and moreover, there's a big idea in Lyapunov analysis that should help us get around this, right? The whole promise of Lyapunov is that you shouldn't have to do numerical integration or any integration forward in time. The whole point is that I want to be able to look at the instantaneous vector field and say something about the long-term performance of the system. That's the beauty of Lyapunov. Instantaneous analysis tells me something about the long term. So how do we take this tool and say something about limit cycle stability using the language of Lyapunov? Now remember, this system, any of these limit cycles, are not stable in the sense of a trajectory, because if I were to be on the cycle, right, you remember the difference between trajectory stability and limit cycle stability. If I'm on the cycle and I got a perturbation, or if I slowed it down, then the points on that cycle will never converge. So I can't expect some function over the whole state space to be decreasing in the sense of Lyapunov. How do I do something better? Okay, the big idea here, so this, R of A of xp, this requires knowing p. And the big idea here that's going to help us get around this is the idea of a moving Poincare section. Okay, so the picture I want you to have in your head is that, yes, I have a surface of section here. Instantaneously, I can say something about the dynamics of that system, of that vector field here. But I'm going to let my surface of section move along the trajectory and try to say something that at all points, I might have a different surface at each point. If I can say something for all of the surfaces of section that follow the trajectory, then I'm going to be able to, if I analyze all of them independently, then I can say something about the whole without having done integration, right? Because I could certainly imagine, just I could have certainly done it with two, right? If I had that surface of section and this surface of section, if I could say something about this and this, that's all good. And just think about having a surface of section. They have to be consistent, of course, with each other. A surface of section that moves along here. And the picture that we like to draw for this is you've got a trajectory here, and there's somehow this surface of section that is moving along the trajectory. Okay? And so this, in my case, is x star t, my periodic solution, and this is, we'll call this S of t, my surface of section over time. Okay, so how do we put that to work? What we're going to try to do is we're going to describe that surface by defining a new coordinate system. One of them is the coordinate along the trajectory. I have x dot equals f of x initially, and I'm going to write a new coordinate system where I define the time along the trajectory, or some surrogate for time. I'll call it tau, and then the other dimensions I'll call the perpendicular, the remaining directions that are transverse to that, the surface of section. Okay. Does that make sense? I can always just pick a new coordinate system for my robot and rewrite it into that coordinate system. And the coordinate system I'll pick is I'll call tau the dimension along the trajectory, right? And then as a function of tau, right, at any given tau, I can define my x-perp coordinate system. Okay? So I can always rewrite my state in that coordinate frame, okay? And I can update my dynamics, my flow on that. There's some flow along tau, which on the nominal, on the trajectory, it's just tau dot equals 1 if I'm moving along, if I've defined it along time. Okay, and off the trajectory, there's some other dynamics, which is the result of, well, I'll work an example so you see what that is. This is called the transverse coordinates for the system. Okay. In fact, the choice of those coordinates, that name is important. The choice of those coordinates is not unique, okay? The only requirement that's going to be required for this analysis, just like the surface of section, is that the vector field has to be transverse to that surface of moving surface of section, right? So this surface of section could be here, it could be here, it could be here, whatever. The only point is that the trajectory coming out cannot move along this section, right? It has to be transverse. The dot product of every vector in this field with the flow has to be non-zero, right? The cross product, did I say that right? Cross product, non-zero, yeah? Okay, so this is the transverse coordinates. The cool thing is that if you can write this transverse system, this transverse coordinates, then there's powerful theorems that link the same type of powerful theorems that work for Poincare analysis, which says if you can talk about the stability of this subsystem, just the transverse subsystem, that it implies something about the stability, the limit cycle stability of the original system. Okay? This is called, this analysis is called orbital stability. Is the idea clear? Because this is the kind of thing that sounds simple. I want to make sure you get this locked in, because once we start writing equations down, you're going to start twisting your head because of the x-perps and stuff like that. So I just want to make sure this is solid. Yeah?
So just to make sure I understand correctly. The extent to which this is specific to orbits is in that we are dropping one dimension from our state fields. So that there is something we don't care about.
That's true.
It is not necessarily that it needs to cycle back.
Good. So I try to be very careful to never use the word stability for a trajectory that only has a finite duration. Those two things don't go together. So typically, when I'm talking about using the word stability or talking about any type of stability, then it means my trajectory has to be defined for all time. That can be true if it goes to a fixed point of the system. It could be that if some finite representation or something has infinite extent. But it's the ones I've restricted myself to are things that are periodic, because then it really is natural to talk about stability of a trajectory.
Yeah, I guess the example I have in mind is from last homework. We had this wheel position that we didn't really care about, and we just dropped it in some way that we feel very flexible. This is the same idea.
So you can do, there's two concepts, right? One idea is that I only talk about stability in terms of, I use periodic solutions to talk about stability because of that technical point. The second thing is that limit cycles, by their nature, have this property that you are not allowed to care. If you tried to say something about the stability, including the direction of the trajectory, you will fail. So the same tools will work to do finite time analysis along any trajectory where you don't care about that one direction. Okay? Typically that direction is time. You asked a question back when we were doing LQR, for instance, the time-varying linearization, right? That if I took my perching plane, grabbed it in the air, pulled it back, it would actually, the stabilization we wrote would try to catch up with the initial trajectory. That's the only way it knew how to do it in that solution. If we wanted our perching plane to not care where it was on the solution, but just look for the closest point on the original trajectory to search over tau, then we could use this tool to do that, even though that's a finite duration trajectory. Okay? Yeah? We're going to talk about the stabilization at the end. So let's come back to that. So this is not specifically tied to orbits until I use the word stability. And then I feel that it is fundamentally tied to orbits. Okay? If I talk about a finite time, did I get to the perch or not? It works for trajectories. So if I care about, did I successfully pick up the mug? That works for trajectories. But I won't use the language of stability, and even the language of Lyapunov requires more details and more care. It's possible to use, but it's simpler to describe in the infinite horizon. Yeah?
So is there any sense of like local or global stability, or is this completely different?
It's completely the same. So, yeah. So local stability means epsilon away from the trajectory. In fact, I think it's my next page. Yeah, I will tell you local stability, global stability on the very next page. Completely the same. And regional is the other one in between. Right? So if you have a region of attraction, that's a regional stability. Okay, so here's the trick. Here's the more general trick. If you can find a function v, which I'll now write down in the transverse coordinates, it can be a function. It's typically a function of both x perp and tau, right? That is v of x star tau equals 0 for all tau. And v of x perp tau greater than 0 for all tau for all x perp not equal to x perp star. Okay, this is a Lyapunov function that goes up, and it's at 0 at the origin. So the picture you should have in your head is somehow, the simplest case would be like a quadratic form that's coming up from this, right? Some quadratic form that's sort of moving along the trajectory, yeah? And v dot perp for all tau, what I only care about is partial v, partial x perp dot, so just the partial derivative in the direction of x perp, and I don't have to worry about how long the trajectory is less than 0. And equals 0 at the origin. Then x perp tau is orbitally stable. Limit cycle stable. Okay? Once again, you can have all the permutations. You can have, if you have only less than or equal to 0, you can have stable in the sense of ISL. If you have strictly less than 0, you can have asymptotic. If you have less than some, some alpha times x perp, you can have exponential. And you can have this over locally, based on, for instance, the linearization, regionally, you could find some set of x perps for which this is true, or global stability. Global's sort of, you never, for a cycle, there's always going to be some singularity or something that keeps you, that forces you to go to some other direction. But you can ask the question, the global questions too.
For exponential, I can't see how x perp, maybe you mean v of x perp?
Sorry, v of x perp, yes. When it's quadratic, it's, yeah. Cool? Okay, so let's make this more concrete with trying to find that limit cycle, find that that function for the rimless wheel. Okay, so I'm going to set m equals to g equals to l equals to 1. Okay, but it's worth it, because then I can just say that my dynamics are just that. Okay. I have my update is just theta dot plus is just cosine 2 alpha theta dot minus. And that happens when theta equals gamma plus or minus alpha, right? And the energy, just so you remember, in this case, is just 1/2 theta dot squared plus cosine theta. Okay. I mean, so we know we have the limit cycle that looked like that. What's the region of attraction of that limit cycle look like? We computed it. We computed it at least on this line, right? And we plotted it as stripes on this line. It wasn't trivial, right? You could actually go uphill and end up going around and coming back and going forward. But certainly, if we just start, there's a point where your velocity got too slow and you started just bouncing around and going to some fixed point over here. Right, so there's some notion that there's some critical energy where if you don't go over the top, you're kind of screwed. So probably this is the boundary of the real basin of attraction. Right? What happens up here? Well, it turns out that for rolling down a hill, no matter how fast you start, you'll always end up rolling. So the basin of attraction goes up forever up here. And then it gets more subtle over here, where you have some states which come around like this and end up being up here enough that they land over here. Okay? So the basin of attraction is kind of a funny looking thing. Funny enough that I brought a plot. I knew my chalk wouldn't do the job. Okay, so this is the slightly prettier version of that transverse picture. Okay, and we're going to try to find regions on that transverse coordinate system that are my region of attraction, which will be defined as a level set of my Lyapunov function. And for the for the van der Pol oscillator, you can do moving sections like that, but we're going to do, this is the rimless wheel, okay? So this is zoomed in to the crosshairs on the eyeball of the pendulum, right? The black line is my limit cycle, which goes back to there. The vector field is plotted for you, although the arrows don't show up on this pixel count, okay? And that's what the pink area is the basin of attraction. Right? So those are the states which were too slow, but they sped up. They went around and then started rolling forward. Right? That was actually going uphill and then came around and go forward. All right, so what are we going to do to try to find the region of attraction there? Well, it's hard using, because of that, because of this thing, it's hard. The tools we're going to do are going to find an approximation, an inner approximation, just like we did in the other case, in the simpler fixed point case. We'll find an inner approximation by finding, let's say, a quadratic Lyapunov function over x. It's quadratic over x perpendicular that moves along, that has this moving surface of section. You see those lines going up and down? And the level set of that Lyapunov function as it moves forward in time is going to look like this. Is that clear? All right, so how do we pick our surface of section? So that picture suggests that actually there's a simple choice of the transverse coordinates. Let's just choose tau. So the black line is my nominal trajectory, x star, right? This thing is x star. I have to choose, tau is some function of theta and theta dot. X perp is some other function of theta, theta dot, and they just have to not line up, right? So the simplest algebra is going to be if I choose tau to just be theta. My notion, I just want something that moves along the trajectory, right? And tau is always increasing along that black line. So let me choose tau equals theta. And I'll choose x perp to be basically theta dot. But because I want it to be centered on I want my quadratic Lyapunov function, let's say, to be centered on the nominal trajectory, I'll do theta dot, but subtract off the nominal, I'll call it theta dot star, which is a function of tau. Is that clear? Right? So x perp is the distance in the vertical plane on that picture from the black line. Okay? So now let's do some of the mechanics, because otherwise you don't really, until you do an example, it's hard to get your head around the transverse stuff. Okay, so what does tau dot look like now? That's just theta dot, right? What are the dynamics on my transverse coordinates? Tau dot is just theta dot. I'm just taking the derivative of that equation. X perp dot is, theta double dot plus the derivative of this, minus partial theta dot star tau partial tau dot, which I can insert here. I can insert the dynamics for here. I can do a little algebra and a little bit of, I have to use the energy to relate these things. And it turns out, after a little bit of manipulation, which is all in the notes, or at least here, is, what do I get? I get negative sine theta over theta dot star tau times x perpendicular. Okay? It's just algebraic manipulation of that derivative. And that's telling me how fast am I going up or down in that axis as a function of tau, right? And theta dot. It just so happens that this system is linear in the transverse coordinates. But in general, I could have asked more subtle questions by linearization. I could ask the local questions by linearization. Everything clear? Yeah? Feel free to ask questions if you have them. Yeah?
Sorry, can you explain why the shift on x perp? Why you do that again?
Because I want to have a Lyapunov function that at x perp equals 0 at the trajectory. Yeah? All right, so here's a super important point, okay? So this looks like, so the dynamics of my transverse coordinates look like a time-varying, if you will, linear system, right? It just happens that way. You don't normally get that lucky. It's also a scalar. right? I could have written this as lowercase a, because it's really a scalar in this case. And it's a scalar that's sort of trivial to compute. Okay, so I'm going to get to ask you some very basic questions about the stability of this system. Yeah?
It depends on tau.
Yes.
It's not really time, right?
Right. So I actually wrote tau varying, and I was debating whether I should write that. It looks a little weird on the board, but tau varying is fine. The orbital stability result says that you can think of this as, tau is time, and infer something about the long-term, the orbital stability of the system.
The dot on the left-hand side of this will also be derivative by tau?
That actually means time. Right, because I took the derivative with respect to tau dot. Mm-hmm.
So there is some theory about time varying systems. It's not quite the same.
So it all works out. So there's a as long as tau dot is increasing along the trajectory, then the arguments about what x dot has to do in time and tau relate to each other, right? By virtue of picking a tau dot that is moving forward, tau dot needs to have a dot product greater than 0 with the trajectory, and the surface has to be transverse to the trajectory. In those cases, you can make this connection. Stability in x perp like this infers stability of the orbital stability of the original system. So the question is, so this thing, it happens to be simple enough that we can think about it. So first of all, x perp dot is always positive in this case, right? The black line, for all tau inside this window, theta dot is greater than 0. We agree? The wheel is always monotonically moving forward. Theta dot is always greater than 0. Okay? So then the stability of this thing, for the one-dimensional linear system, I can just look at the sign of this thing, right? So it turns out that a tau is actually greater than 0 with theta less than 0. A tau is less than 0 with theta greater than 0. So the stability of this orbit is quite subtle, and it's just really important. So it's actually locally expanding. The vector field is expanding when theta is less than 0, right? Trajectories are actually diverging in the transverse coordinates, right? If I watch 2 points in the perpendicular coordinate, how they evolve in time, they're actually moving apart until you get to theta equals 0, and then they move together. So of course we know that the rimless wheel is stable, and we already said that's the Roux basin of attraction. But my Lyapunov analysis to capture that has to have a function which changes over time, so that's why the level set of the Lyapunov function is actually getting bigger to begin with, because it has to allow, in order to always go downhill on my Lyapunov function has to stretch out faster than this thing is expanding. Okay? So the boundary of that basin of attraction is pulling out, and then it's coming back in as it's able to in order to form a closed circuit. And if I take the boundary of that purple region and multiply it by cosine of 2 alpha, I have a consistency condition back I better get the same thing on the other side. Okay? So this is really cool. This is true in the trajectory case or the periodic case. You can have systems that in the short term diverge, but over time, ultimately, the integral of the total solution gives you something that performs well over time, but instantaneously, you're actually losing control authority. And that happens all the time in legged robots. So certainly, for instance, in running robots, once I leave the ground, I don't typically have any stability, right? I have my dynamics are governed by orbital mechanics, I guess, if you will, right? So just free-floating dynamics, right? I can't change my angular momentum, right? So it's hard to be stable in the air, and typically these running robots are losing stability in the air and then having to do something during the stance phase to regain stability, and it's only over the entire cycle that the system becomes stable. Okay, and that's a really important thing. Same thing with the perching plane. There were times in that trajectory where there was very little control authority. But there were enough times where it had control authority that the whole system could remain inside some funnel. The funnel had to get bigger or smaller over time in order to compensate for that. Okay, now you can imagine for these conditions, I can, for more complicated surfaces of section, I can still run some machinery to figure out what my new vector field looks like in the transverse coordinates. And you can imagine, and we have written sums of squares programs to compute that, for instance. So I come up with a Lyapunov candidate, and then I use sums of squares to find to scale that candidate to find the largest possible region of attraction that's satisfied by that candidate. Typically, we cheat a little bit and sample over time and just verify the condition at a finite number of times, because the dependence of V on time is typically complex and requires very high degree polynomials to capture it well. I'm okay sampling over any one dimension. Sampling in high dimensions sucks, but sampling along one dimension is okay. So those lines are actually where we sampled that. And we ran sums of squares, given the equations of motion in the transverse coordinate, in order to come up with that region of attraction. There are some additional things we've done to make this work better. It turns out your choice of coordinate system can affect your success in finding regions of attraction. So we have actually an outer loop optimization now that searches for the transverse coordinates by changing tau to not necessarily be perfectly lined with the trajectory, but around it, and then picking just some orthogonal coordinates around that and moving that around. And we're able to get bigger regions of attraction by doing that. Okay, it's all in a paper if you like, but I really just want to give you the bigger picture idea is that you can actually do sums of squares along a trajectory, even through impact and through collisions, if you handle it all right. For the compass gate, the nominal trajectory, which I realized I forgot to put, it was like my next slide on last time, I forgot to draw it, but this is the swing leg going across the top. It covers this huge blue arc out of state space. Then there's an instantaneous collision. It turns into the stance leg, moves around, instantaneous collision goes around again. And then you could ask, what is the region of attraction of the compass gate? And you can use, we cannot integrate those equations over the time, but we can come up with a Lyapunov candidate that moves along the trajectory, and we can verify that with sums of squares. If we write down, we still have to know the reset map, and we project the Lyapunov function through the reset map and do its thing. For manipulation, you could do the same thing. You can ask, is there a function for neighboring trajectories around my plan, I end up in a good region after executing the maneuver, right? Lyapunov gives you the ability to talk about not just single solutions, but robustness of a tube of solutions. It's a very powerful idea. Okay, so the last thing I'll mention here, so we got lucky here in that the choice of coordinate system, it ended up that the time derivative in the x-perpendicular was linear. But in fact, if it was something else, if my dynamics in general were this f perp, some nonlinear function of my transverse coordinates, linearization of this function still tells you something interesting. Many of the tools still work, okay? So, approximate this by some A of tau x per bar, let's say, then I basically have a time varying linear system on my n minus one dimensional system. If I want to come up with a Lyapunov candidate to start my analysis, I can solve the Lyapunov equation on this linear system backwards in time, right? So I skipped over it, but let me. It turns out I can solve the Lyapunov equation and in the case of a limit cycle, I'd like this. I have to have this this periodic solution. This Lyapunov candidate has to be periodic. And of course, it's positive definite, symmetric. Okay, so just like I solved the Riccati equations backwards in time to find LQR solutions, I solved the Lyapunov equations over time to find an initial time-varying Lyapunov candidate. Here in the limit cycle case, or in the orbital stability case, I can find an initial quadratic Lyapunov function, right? So this is my x perp tau is x perp transpose p tau x perp, right? And I can do it by solving this equation backwards in time. I can also do LQR on the transverse linearization. I can, if I have a control system in my perpendicular coordinates, I get ax perp plus b x perp, and I can design a controller that stabilizes my trajectory over time or over a cycle by integrating the Riccati equation backwards in time. And it works, right? So let me show you a couple examples of it working. This is actually the compass gate that we built a while ago. This is kind of fun. It's like a blast from my past. But in fact, yeah, so before the toes work, you have to put blocks down, right? But then the toes work later. But the reason I like to show this one is you can sort of see Zach. That's Zach Jakowski. He did his master's building this robot and a bird for us. Now he's the lead designer on the quadrupeds at Boston Dynamics. He's awesome, even though the toe fell off in that particular video, right? So we built a series of these compass gate walkers that were where we did trajectory optimization to design the nominal limit cycles and the nominal gates. We did a transverse linearization to stabilize those limit cycles, to design a control input that varied over the period or over the trajectory to give long-term orbital stability. And we even did the region of attraction analysis like you saw. We had a series of walking robots that would fool around lab and that was an earlier one before Zach built a cool big one. This is still trajectory optimization through contact. The way we figured out how to make Atlas run inside torque limits in a simulation was trajectory optimization through contact, just like I said, with a couple tricks to make it scale well, where we only thought about the center of mass dynamics in second order, and we put in the kinematic constraints. But there's some details just to make it lower dimensional and to make it to have less local minima. But basically, that's trajectory optimization. Take the same algorithm, you put it down on a quadruped, and you can start designing gates. If you choose a certain ordering of feet, a certain mode sequence, you get trotting. If you do a different one, you get galloping. This was literally the same algorithm that ran. One weekend I was like, I'll just try all these different gates, and then it worked. Okay. And then this is Atlas jumping off a block, which, so we were terrified of breaking Atlas the whole time, because especially before the competition, like if that robot breaks, we're screwed, right? But there was this really fun day. There was one magical day where Boston Dynamics said on November 22nd or whatever, you're going to ship your robot back to us. We're going to do a big upgrade. And we thought, on November 21st, we're going to try to jump off some cinder blocks, and we did. We never landed it, and I don't have the great video for it. But that robot, that trajectory has been executed on the real robot. It was torque feasible. All right, cool. I will see you next time.